Hello, so we're going to be solving some dimensional analysis using the Sherwood-Gilligan expression. We're going to be using two regression methods to find the Sherwood numbers, and we're going to also fit the data and plot it on a 3D plot. But the first thing that we need to do is we need to input numpy as np, and that will allow us to use numerical calculations in Python. And from the scipy.optimize, we're going to import minimize. And what that allows us to do is use the least squared method in Python. So we're going to import plotly dot graph objects as go. And what this will allow us to do is will allow us to make 3D plots in Python. I knew I was wrong on that one. Okay, and we're also going to change the theme from the white color to the dark color. So po dot default color. We're gonna make it dark. So we're going to generate some random uniformly distributed numbers for the Reynolds and the Schmidt number because we don't know the exact numbers. So we're gonna generate it from the lower bound from the Reynolds number to the upper bound. We're going to do it for both the Reynolds and the Schmidt number. So the Reynolds number np dot random dot uniform, and we're going to it's going to be randomly, uniformly distributed between 2,000, 3,500 to 3,500. And we're going to make that 100. We're going to make that 100 data points. And then for the Schmidt number, we're going to also do the same thing, but we know it's from 0.6 to 2.5, and we're going to make that about 100 numbers. And we know the Sherwood-Gilligan expression that was in the book that we're trying to solve for times RE times 0.83 times SC times 0. Okay, and now we're just gonna add the experimental error data. The shared number is randomly randomly distributed, and we're gonna want the mean to be around the Sherwood number, and we want the scale to be about 10% multiplied by its own number. Oh, we want it to be uniformly distributed. No, randomly. Normal. Random dot normal, right? That's what I said. Local equals SH scale. Oh, that's it. Okay. Now, we want to make a design matrix and stack the columns on top of each other, on to the side of each other, stack them for the Reynolds, the Schmidt, and the Sherwood. So what we're going to do is we're going to make a design matrix. We're going to make it np dot column stack np dot make the shared number ones, and we're going to make the log of the Reynolds number and the Sherwood number, or Schmidt number. This should be cool. You know what? Okay, so we have the unknown, and we're going to be using linear algebra to find the transpose of the design matrix. So to do that, we're going to do random np dot lin algebra dot inverse. We're going to do the inverse of the design matrix and its transpose multiplied by itself, its own design matrix. And then we're going to multiply it by its design matrix, multiplied by its transpose again, and multiply it by the log of its Sherwood number. So we're going to look at the Sherwood number. We're going to look at the unknown number, actually. So we found the numbers to be relatively close. 0.83, 0.84, that's close. 0.44, 0.444, that's close. But this one wasn't close. It's because this one we did ones like. So we're going to take the exponent of it, np dot exponent. And we're going to get it in the first of its array. We're going to do the first element of its array to the exponent, and that should give us the number 0.019. That's pretty close. So that was the first regression method to find the three numbers. There's another method. It's the method of the least squares. And to do that, we're going to define a function called sum square. And we're going to name it A. And we're going to return the sum of the Sherwood numbers minus the first element of the function. Multiply the Reynolds number multiplied to the power of the first element, A1, and then we're going to also do it for the Schmidt number.
I didn't get that. Could you try again?
We're also going to do it for the Schmidt number multiplied by the second element of the array. 0, 1, 2. Yeah, second. Third, actually. Because when in Python, we're going to multiply it by 2. In Python, the first element of an array starts at 0, and the first element starts at 0. The second element starts at 1. The third element starts at 2. So that's how it works. So now we're going to use the minimize function for the sum square. And we're going to use 3 guesses. So we're going to get 0.19. We're going to make it really close to our numbers, 0.84. And then 0.44. Oh. Okay. So we found the numbers. So these were two ways to get the Sherwood-Gilligan expression. The first method by making guesses, and the second method. So now we're going to make a 3D plot.